Hey everyone, today's lecture will be on circuits. Just generally, so um, more specifically, it's not gonna be more of a worked example kind of thing, but it's more gonna be an overview of like what you should know, to answer questions and the type. So, circuits. So, I think when you first approach circuits in physics, it's gonna be mostly like electrical circuits, like what you would think of when you think of like when you say circuits lah. But in general, circuits are kind of just any network that has any interacting features. Like these could be gene networks. These could be like circulatory circuits. These could be like um, what's it called again? Like supply chains and stuff like that. I think I don't remember what it was called, but it's like some economic model where you can like model inflow and outflow. Um, so anything that you can model with like as a network and has some flow and some potential, then it is a circuit. Um, so yeah, specifically in physics, like over here we only talk about electrical circuits. So I mean, which is like basically most of the case because um like it is quite a revolution when you turn from that's why everything got smaller. That's why the digital revolution happened because everything turned to electrical circuits instead of like mechanical, like punch cards, for example. Everything just switched from that into like electrical stuff. So mostly we'll be talking about electrical stuff circuits. But yeah, right. Remember that like this is more general. The stuff that we learn, the stuff that we model. More importantly, don't like throughout this lecture, don't miss the trees for the forests because these things can apply to like many other things. Um, okay, I have a list of stuff I want to talk about today. All right, so firstly, physical meaning of voltages and currents. So circuits, as I said, it's like any generic network that has like flows and whatever, right? Suppose there is let's see okay, wait, I don't have a good example. Sure, let's just use a normal circuit. So I have a resistor, I have a battery, I have a capacitor. This is some random circuit I just kind of made up. Um, so for this one, some people also like voltage. I mean, some people draw things differently, but like, this is just how I draw it. Like it's okay if you like, because batteries sometimes people draw it like this, one long, one short. But I may or may not confuse it with capacitors, so I'll just draw it like this as a voltage source. So, um, yeah. So in circuits, we have two important quantities. For every component, we have the voltage. So over here we have some voltage source, and we have currents flowing through everything. So currents through the resistor, current through the capacitor. So um yeah, so voltages voltages is energy per charge. One of the things that we realize, again, remember that don't lose the trees for first. Like charge can be anything at all. Like charge can be um gene or like mass or like just anything that's like normalized to like one particular thing. And like it's a total potential energy divided by total electrical charge in that's being carried around. So this should be from last week. Um it should be from last week. It's just something that we like borrow from EM. It's not a circuit thing per se, so it's a general like physics EM thing. Um, Current is the charge per time. How much charge moves through this one point per time? So actually, I think I kind of lied. I kind of lied. So voltage doesn't actually exist. Well, okay, voltage does exist in the sense that if so, okay, well, I'll say why yes and why no. I claim that that doesn't like the absolute quantity V doesn't is not useful. What's more useful is delta V, the change in energy per charge. So voltages are always defined between 2 points. Currents can be defined on one point. So, for example, here. it's not really useful to talk about voltage. So for example, when you talk about this battery here, this battery, like you can say, so like people say that, okay, the voltage is V, but how you actually use it in circuit is that you say that the difference between these 2 points, the voltage difference between these 2 points is V. So that's more useful. That's more of a useful idea that we should have, like instead of like having just like voltages, because absolute voltages don't really exist. Same thing in potential energy. When you learn gravitational or potential energy, when you learn gravity, um, you learn that like, U is equal to negative G M over R, and then like um, so this U um is actually relative to infinity. So let's say like R equals infinity point where like U equals zero, and everything is like relative to that. But actually no, like that's a bad example. Let's talk about like MGH lah. Okay, MGH is a more useful example. I realized halfway through that example is not that good. So in the case of gravity, like this is more like the useful form of potential energy. You can say that U equals mgh, but then that means that when h equals zero, U equals zero, which is okay. It's fine. Like it's totally fine for h equals zero to be U equals zero. But then like like below h you get negative U, which is also fine. It's just that like mathematically, like physically it doesn't like the universe doesn't give a shit. Like the universe doesn't care like where you call h equals zero, as long as it's consistent with this delta U. Like if you go up, the potential should decrease. Sorry, should increase because like well, you get higher the more energy you have to drop. So as long as you keep this ordering of potential energy, as long as you keep this ordering and scaling, wherever you call 0 point doesn't really matter. The universe only cares about the ordering and the scaling. Um, so the magnitude lah. Um, so yeah, like that's a so over here coming back to circuits, like delta V, the change energy is what's important. Like they don't give a shit about like what absolute voltages are. Sometimes you'll like see people sometimes you'll see questions like this. You'll see questions like, oh, I have a sphere, I charge it up to some I charge it up to some charge Q. If it's an conducting sphere, like what's the potential on the surface? Then when people say potential on this in this kind of sense, so like this is not really circuits. You won't really see stuff like this in circuits. So when people ask you like, okay, I have a conducting sphere, I put charge on it. What's the potential on the surface? So in this case, people would take potential to be relative to infinity. So at r equals infinity, v equals zero. At r equals r, v equals what? So it's like on the surface of this like conducting sphere, what's the potential? So that's what people mean when you ask like if you quote voltages without any if you quote voltages without any like reference point, it's always like relative to infinity. So is that okay? Does that make sense? Everyone okay with that? Cool. Because I know like when I first learned about like negative energy or like this kind of like then, like what does the universe care about then? Because like if you can just set anything to be zero, then like what does the universe care about? So the universe doesn't care about like where you set zero. The universe cares about um things relative to that 0 point. Like how is that thing being relative to? Um, so yeah, like the ordering, like as in it should increase as you go away or decrease as you go away. That ordering and also like the magnitude. Like so so sometimes things in circuits can get really counterintuitive. So at that point, just I would like to think of like the gravitational examples. So let's talk about a simple circuit. Um, so the most simple component that people can have is a resistor. So what does a resistor do? It resists. Okay, again, it's kind of counterintuitive because like everything that we do, um, so everything that we do in electrical circuits, it's kind of like using a component that takes away energy. So like I mean like at first lah, like afterwards you like take electrical engineering courses and then you realize, oh, like you don't just have to like dissipate energy. So it's like it's like a toy model kind of thing. Like you learn it's like a intro circuits kind of thing. Like at some stage, like resistors are only there for like picking values, like where you really have to dissipate energy. But most of the time, people don't use resistors for like actual designs. I mean, like not as like they're not the core part of the design, lah. But like in kind of like circuits in physics Olympia, we just kind of like it's easy to like model. Um, so suppose you have some battery with voltage V, and you will normally see resistors with resistances R. So let's talk about what a resistor is. So resistors are really easy, like um, one of the first things that people would think to model because basically what it does is you have a material, you have a material. Back when people still think electrical circuits, sorry, electrical currents were carried by actual electrons flowing. I mean, people still do, like, as in the pipe idea, like the pipe model. Um, so wires or like materials have stuff in them. So these are atoms, these are like stuff. So these are like things. So as an electron, when you come in, you will bump into things, right? You'll bump into things. So um and then, so if you don't apply any electrical field, so if the electron is not being accelerated, the electron will just kind of like randomly walk. So if you don't bias this, lah, if you don't tell the electrons that, hey, move to the right, they won't move to the right. They will just randomly bump around because of thermodynamics. So like this guy will go here, this guy will go here, this guy will go here, this guy will go here. So the total effect is that everything just zeroes out. There will be no net electron movement. Everything goes everywhere all at once. If you take the average of everything all at once, this is zero. So, but once you apply an electrical field to it, so notice I say field. It's not a voltage. It's not a force. It's a field. So, if you apply a field across this thing, so once you have a field, like everything starts like being biased. So there's a preferred direction to every um there's a preferred direction to like the flow of electrons, and they get accelerated more and more as well. So the more electrical field you have in this model of a conductor, at least in this model of a conductor, then you have more and more flow. So how we describe this microscopically. So this is the microscopic model of conductors. Microscopically, so the flux of electrons. So electrons per time per area. Electrons per second per area. So why do we normalize by area? Because like, we don't want to talk about how big this conductor is. This conductor can be um, conductor can be that big. This conductor can be this small, but the effect still holds, right? The effect still holds. Like, where you have to when you apply the electric field, the electron should still like, have a preferred direction. Something else that might not be this kind of model would be stuff um like transistors or like diodes or like stuff like that's like nonlinear. But actually like capacitors, well, I mean like um different models of so because different models of matter can give you different types of components, and in this case we will get a resistor as you'll see. So over here, um for a resistor, um it doesn't really depend on area. I can't think of anything that would depend on area, but so yeah, so this is called the current flux. So electron charge actually. So instead of electrons, let's say charge per second. Charge per second. So this is the current density, um, and this is equal to. So this charge per second per area increases linearly. It's like increases as the electric field applied is like getting greater and greater, right? So the more electric field you apply, the more they bias the general directions of the electrons, and they move to like one preferred direction. I realize that I'm drawing E to the right, so these red things are like positive ions. So if you if you want the positive charges to move to the right, then you apply this field. If you want the electrons to move to the right, then you apply this field because electrons have a negative charge. So yeah, I realized my mistake halfway through I saying that. But like it's a positive negative charge kind of thing. So so microscopically, if you just say that they increase linearly as the electric field, they may not. So the thing is, once you actually do like the actual like thermodynamic analysis of this with like mean free path and whatever, then you will get like a linear situation with some assumptions. But over here, I'm just gonna give it to you guys that it's like gonna be proportional to the electric field. And there's this one more term called the conductance. So this is the conductance, or was it susceptibility? I don't remember. It was like so I think this is conductance if I remember correctly. So so every material is gonna be different because if these like atoms that the electrons bump into, like if they're really, really big, then like they bump into more per time. If they're really, really small, they don't really bump into a lot of them. So this conductance is a material dependent thing that people just measure. I mean, you could like have models of materials, and I think that's what material scientists do. They measure a lot of conductances. Um, but yeah, generally what like for physicists we just call them like a constant like a constant scaling factor lah. It's just like some number. So yeah, altogether, J equals sigma E is what governs all conductors. Yeah, all conductors at all. So um, yeah, remember that this is also the field. So this is what we call like microscopic Ohm's law. So microscopic mean in the sense that we're looking at individual particles at this level, at this like fine grain detail. Um, we see like so much, like we see this law called like we see this relationship. Um, But like we can't really go to the level of electrons, right? So what we can observe instead is the total effect of all this. So if you kind of like zoom out, the same effect will still hold, which is interesting. Like that doesn't normally happen. That doesn't always happen. Like you expect it to normally happen, but that doesn't always happen. Like having a microscopic law doesn't always translate to like a macroscopic law. So, but anyways, like if you in this case of Ohm's law, it does, and the macroscopic Ohm's law. Macroscopic Ohm's law is just the current is equal to 1 over R times voltage. Um, or basically V equals IR, lah, like the normal version that you'll see. So um, yeah, that's how Ohm's law comes about because of like the model of conductors that we have. Okay, so any questions on that? So that's the first part of like introducing these parameters, introducing like coming from last week's lecture. Any questions on this? Okay, cool. So next thing. So now we're past this understanding where we're at, like bridging from last week to this week. Let's look at like how we can analyze circuits. So let me pull up a circuit example. Yeah, so I have this list and I have like a document of like stuff that I want to talk about. Um, I haven't really had time to like write the handouts yet this week, so my bad. But I did prepare this lecture. So, okay, so um, mm, this one, no. Wait, you know what? Let me just like make up a simple example. I mean, it's not worth it to like get a really specific because it was like something that I already solved. I just like put it somewhere, but you know what? It's fine. Let's make something up. So I think this is a good point to also introduce you guys to something called a current source. So I know like as physicists we normally just look at voltage sources and call it a day. But to electrical engineers, like current sources are also really important. Um, well, the thing is like you do so many practice problems with like voltage sources that um when you have a current source, it's like, oh, I'm not that familiar with this guy. But actually, like they're the same thing. They're like exactly the same thing. As in, so for a voltage source, it constrains the voltage but doesn't limit the current. So the voltage source, so as in the voltage source only imposes so I mean before as a small aside like before I continue, the voltage source doesn't give a shit how much current passes through it. The voltage source is only there to make sure the potential between these two ends are constant. Or like it's whatever it says that. So like it's V. So the voltage source, the job of a voltage source is only to make sure the voltage difference is V. It sounds very trivial, I know, but like in a current source, so as in, like the current do this unconstrained. So as in, like it can be just whatever value it is. Like for example, it's a resistor. Like think of a resistor. The resistor doesn't really constrain the current. The resistor doesn't really constrain the voltage, but it does. What it does constrain is the ratio. The ratio of V over I has to be the resistance. So for a resistor, it doesn't really care about like it can't really control what current goes through it. It can't really control what voltage goes through it. But what it can control is that R is V over I. The ratio has to be controlled for a resistor. Like the resistor fixes this ratio. The current source, sorry, the voltage source fixes the voltage difference. Um, Let me just put this here. So this is constrained. This is constrained. For current source, the current is constrained, but the voltage can be whatever value it is. So it can be like it's like it doesn't constrain the voltage. Oh shit! Oops, wrong color. Yeah. So just keep in mind like that's how these components work before if you haven't seen them before. So let's see 2 6 2 12 volts 2 ohms. Shit. 6 ohms, 2 amps. Okay, so let's see, where are we at right now? So, oh shit, notes. Things are not going well. Okay, well, so, um, oh, wait, actually, one more thing I want to talk about. Sorry, I just realized I skipped this in the mid thing. So, notice how I'm drawing these components. Notice how I'm drawing these components. So, actually, no, wait, let me, so, the way I'm drawing all these components is that so many components that we will see have two terminals. Many components that we will see have two terminals. And actually no, like it doesn't just have two terminals. Everything that we will analyze will have two terminals because remember, voltage is the difference between energy, right? Like it's the difference. The difference has to be between 2 points. So like everything that we see will have two terminals. Even if wait, do we have a three? Like I mean, like transistors, but like that doesn't really count. Anyways, yeah, don't worry about it. So yeah, like most things that we will see have two terminals, and the convention that people use is called the passive component convention. Like you just assume like you can use any convention you want, it's fine. But whenever you see like some random convention out of the wild, some random notation out of the wild, um, they use the passive component convention. So basically, you have something, you draw a positive and negative. It can be anything, like it can be this way or it can be this way, but just be consistent. Like for example, okay, for a counterintuitive example, I will choose a battery that's the Terbalik battery. So I know it's gonna be confusing, but like, hear me out. So the passive component convention says that you randomly choose a positive or negative, or like just a direction. So suppose I choose this. So we call this like V in your, I mean, in your, if you analyze the circuit, you will call that V. So suppose this is like an actual battery that's rated at 3 volts. So suppose this is a 3-volt battery. Then V will be negative 3 volts because it's terbalik. So that's V. Um, and so so okay, wait. So you choose a positive and negative. The I would go the current will flow from positive to negative. The current will flow from positive to negative. And so this would actually yeah, so sorry. The current will flow from positive to negative. And yeah, yeah, sorry, yeah, that's it. Yeah, that's the point. The current will, like, if you use this convention, then the current will flow from positive to negative. So whenever you analyze a circuit, for example, over here, the first thing that you do is like assign like directions first, like by vibes. You don't have to know what direction the current flows in, but by vibes, you should like assign every component like a positive, negative, positive, negative. Um, so yeah, that's how this is done. Okay. Um, but yeah, so far, like, if it's is it okay? Like passive component convention, passive sign convention. I think Google, this is what Wikipedia says. Uh, cool. Let's make sure. Yes, exactly. So, also, like, one more thing is that this is the voltage drop. This is a voltage drop. So this is a drop. So no, technically this would be the negative in this case, but yeah, it should be the voltage drop lah. So okay, so um the next point. Okay, solving circuits. So suppose you have some circuit that you want to solve. Some network of components that are connected together. Again, as I said, the first step is like just randomly assign positive, negative, positive, negative. Um, so over here, I'll assign this positive, this negative, this positive, this negative. I don't know. I'm just randomly assigning it. Um, we have 4 components here. Let me check what it was called again. Um, is it this one? Oh my God, Adobe. No, Adobe. Hold on. Bruh. Okay. So we have 4 components here. Okay. So I want to look at the notes that had this. Because anyways, we have 4 components here. And we have 2 unknowns per component. Right? We have 2 unknowns per component. So we don't know the voltage and the current. Like if you just like forget about like all this information that we have, if you forget about all this information about the circuit that we have 4 things that we want to know: the current and the voltage across all 4 components. So we have 8 unknowns. If we have 8 unknowns, we need 8 equations to solve them, right? So 8 unknowns, 8 equations. So what you have, so okay, we have 8 unknowns, um, but then we don't just don't know anything about the we don't just don't know anything about the components, right? So for example, like this current source, like of course it just limits the current. This voltage source, of course, it just limits the voltage. So as in, it doesn't like we don't just not know anything. So we have 4 equations that we already know, right? From this, like think about this. think about the stuff that we have on the top left. Like we have four pieces of information already. So we need four more pieces of information. So for this, we turn to the nodes. So how many nodes do we have here? So when we say a node is a part of the circuit that's connected together. So part of the circuit that's connected together. So if you learn graph theory in like SPM math, I think SPM math they talk about graph theory, right? Pure maths, I think. You guys take SPM? CSC lovers here. Okay, okay, yeah. Um so the graph you have like nodes and edges. So there's like node one, node two, node three. So and then you have edges and whatever. So these nodes, okay, so like these edges are actually components here. These edges are components. The nodes are the voltages. So if I label here, so there's one node here, there's two nodes here, there's three nodes here. Grr. Um, okay, and I claim, oh, that what? Um, yeah, so I claim that there are gonna be, wait, is this true? Yeah, anyways, so over here, like there's gonna be n equals three nodes. But I claim that you only have like n minus one equations. That you only have n minus one equations. Um so we have n equals three nodes, but we only have like so, minus one equals two pieces of information. So remember what we're counting here. We have eight. So remember what we're trying to do here. I'm trying to show you guys that like every circuit that we have, we can still solve because um I'm trying to count how much information that we have and that we need. So currently we need eight pieces of information because we have eight components. As we need eight pieces of information because we have four components. Each component has a voltage and a current. Okay, um so we have so from eight components we drop it down to four because every component we know how they behave. A resistor limits the ratio. A voltage source limits the voltage, a current source limits the current. So drop it down by four. Now we count the number of nodes. So even though we have three nodes, we claim that there's only two pieces of information. It's a higher level, like once you write down the equations. So the thing is like once you write down like the equations for three nodes, and then you realize that oh like they're actually linearly dependent. So that's like they're actually the same equation. It's hard to talk about why at this stage, but if you take like some general linear algebra textbook, if you take like a graph theory, like linear algebra, like they show you why. It's because like what the one liner here is that like the fact that the whole graph is connected, the fact that they're all connected means that you already it's like there's this one degree of freedom that you lose. Like the fact that you have a connected circuit tells you that oh you actually know you actually use one piece of information already. So that's why there's like n minus one. It's kind of funny, like I know it's kind of funny, but like, like there's only n minus one pieces of information here. Okay, finally, there's also so okay, well, a little bit of aside, like how do we write the equations for the nodes? So this is Kirchhoff's current law. Kirchhoff's current law. So Kirchhoff's current law says that if you have one node, the current going in is going to be equal to the current going out. So I out is going to be equals to I1 plus I2. So yeah, that's just Kirchhoff's current law. So like you write the conservation of charge on the nodes. Conservation of charge on the nodes. So if you have three nodes, you would think that you can write three equations, but then afterwards you realize that oh, only two n minus one of them are linearly independent. We want independent pieces of information here, so that's why yeah, n minus one. So anyways, so we can also write Kirchhoff's voltage law. And so Kirchhoff's voltage law um would give um so What does Kirchhoff's voltage law mean? Kirchhoff's voltage law is the conservation of energy. So if you have some mesh, some network, maybe there's a battery here, maybe there's a resistor here, maybe I don't know, there's a capacitor here. It doesn't really matter. As long as so suppose you're an electron. Suppose you're an electron. Electron chan. So electron chan starts here. Um, so the electron goes around the loop, and when it comes back, it should be at the same point. As in, like the electron shouldn't, like this electron, it should still be in the same, like it shouldn't gain any energy from the fact that it traveled around the loop. So by virtue of going around the loop, the electron should not have gained any additional energy. Like over here, it might gain some energy from the battery, lose some energy here, some time dynamics here. But when it got back here, it should still be where it started. Otherwise, if you have gain energy, then you can just keep going forever, and then you get infinite energy. Which is, like we don't really have infinite energy here, so yeah, that's why, there's a conservation of energy here. So it's a mesh thing. So if you have any loop at all, so this should hold for any loop. So over here we see that we have two loops. So we have like one loop here. Sorry, we have three loops. So one loop here, one loop here, one loop here. Um, how many pieces of information do we have? We actually only have two independent loops. So one loop here, one loop here. These are independent loops. The big loop is just the sum of the small loops. So yeah, the small loops add together to make the big loop. So we want independent pieces of information here. So again, from graph theory, you will have so this is actually a really cool trick. It's a really cool party trick. So it actually comes from Euler's planar graph formula. So like you guys ever heard of V minus E plus F equals 2? I think in high school they teach this, right? I'm pretty sure they teach this in high school. Have you guys heard of this before? Yeah. So so there's how many faces do you have? So this V is actually like the number of nodes that we have, because V here is like the number of nodes here, right? The fuck. Fucking America, bro. Like, so the V is some guy was like yelling and like honking at someone. Anyways, so V is the number of vertices that we have, number of nodes. E is the number of edges that you have. Um, and F is how many faces in the graph do you have. So like over here, there's like one face, two face, and there's also like a third face, like that's like outside. So like the outside doesn't count lah. So here we want like number of mesh plus one. So M is the number of meshes. Mesh is sorry. So mesh is whatever we call this. So this what we call a mesh. This one we call a node. So the cool thing, like how can you count how many meshes there are? It's a V minus E plus F thing. So this is a cool party trick. You don't need to know this for the like like this is some like fun fact, that kind of thing. So so once you rearrange this, you get B minus N plus one. So in our case, B minus N plus one is exactly two pieces of information. So we know four pieces of information, two pieces of information, two pieces of information. So like altogether, we have eight pieces of information that we can solve for eight unknowns, and the circuit can be solved. So what I'm trying to say is that like whenever you have a circuit, it can always be solved. If you like just so because like the thing is, why do I say this? Because like okay, suppose you have some general circuit. You have B some general circuit. You have B components and nodes. Like as in like the way you connect them is like and nodes lah. Then you will always have 2B. So this will always be 2B because every component has like voltage and current. And then you add all of these together. B plus n minus 1 plus B plus the difference. So like if you add all these three together, you will get like 2B as well. So you'll always have 2B unknowns, you'll always have 2B equations, and you can always solve that. Um, so yeah, that's my spiel here. Generally, people don't do this. I'm just showing you guys that you can always solve a circuit. Even though it might look like you can't, like mathematically you should be able to. Like unless you're missing. Um, so I think this is like a good diagnostic for when you're solving a circuit and you realize like, I don't remember if I've written enough KCL. I'm not sure if I wrote enough KVL. You can always come back to this and think of, okay, how much KCL should I need? how much KVL should I need? So am I missing anything else? So like, yeah, like this is a good diagnostic table. So yeah, hopefully you guys can internalize this. I mean, you don't need to like always use this method. Like I'm just saying that it's a good check. It's like dimensional analysis. You don't have to like check all. I mean, you should like you don't have to check all your units at every step along the way. But you know, like if you do, then you have a lot more like you less mistakes, uh, better insight, like stuff like that. So anyways, coming back here, what people generally do is using the node method. So this is the brute force method. You write down V and I for every component, and then you just solve the eight equations. Brute force. It's kind of hard. It's kind of hard. Like how do you solve a system of eight equations? I mean realistically, there's like four equations here, but like how do you solve that? Um, so it's kind of pain in the ass. We don't do that. What people normally do is use the node method. So let me copy this. Um, talk about the node method. So what is the node method? The node method, in short, hinges on the fact that like voltages are always relative. The universe doesn't give a shit of where you call 0 volt. The universe doesn't care where you call 0 volts. You can call this node so actually no, I should have erased it. So since we're talking about node method, we should need the nodes. Okay, so node method. We have three nodes here. Um, the node method is a powerful tool that reduces to only n minus one equations. At the end of the day, you only need n minus one equations. Everything else, like it's perfectly labeled. Everything else, like, okay, so you go from it's like a big complexity shift. Like you go from 2b all the way down to like n minus one. So you save a lot of time. Um, so the node method works by since voltages are always relative over here from a discussion earlier. Remember this discussion earlier? Like voltages are always relative. Um, so we can just kind of choose anywhere in the circuit to call zero. You can call this you can call this node zero, and then you can solve for everything else. You will still get the right currents. You will still get the right voltages. Because at the end of the day, this component only cares about the voltage difference between this and this. This component only cares about the voltage difference between this and this. So yeah, it doesn't really matter where you like it doesn't really matter like where you call like the absolute voltages. So over here, I would like to call this as V equals zero. Why is that? Because actually, you know what? Like to be controversial, I can also just call this as V equals zero. So like you can call any one of these V equals zero. But I mean, again, you can't call all of them simultaneously, lah. But you can call one of them V equals zero. So if I call this equals V equals zero, um, so if you call that that node as V equals zero, it's really convenient because now this node up here is going to be V equals 12 volts. And then there's going to be some unknown voltage that I'm just going to call E. So yeah, so now like you realize that if you have a good choice of the node, if you have a good choice of 0 point, um then uh like um yeah, so for example over here, if you have a good choice of a 0 point, then like some points you can just see right away what the voltage should be. Because there's a voltage source. It constrains the voltage. Like we don't talk about current at all here. So like if it's current, then we don't know. If you have if it's current, then we have no information about this node. But we do have information about the voltage source. So like, it constrains this difference to be 12. So um okay, so what people call this method, like as in like when people like say or set it equal to zero, what people actually say is like ground it. You actually ground this. So you ground this circuit at this node. So, um, I think what's something funny about this is that like I think it reminds me of this example, because over here in the case of gravity, you call like the infinity as a reference point. Infinity you call zero. But for electrical engineers, like, if you like something that has no potential, like it's like what people call is that the Earth. The Earth is like practically so the Earth is practically like charge neutral. It's not really. but like it, relatively quite is. It's not really. So people say, okay, you know what? Since the Earth is kind of neutral, let's just like put everything, put our electrical things relative to the most neutral thing at all. And then so they just like literally back in the day they stuck like electrical pipes into the ground. I think they still do. Um, I'm not sure how they do it actually right now. But like, historically, like the reason why it's called grounding is because they actually put like electrical sticks into the ground and then like because the ground is like conductive but it's neutral. So like it's like a charge buffer. So you know how like in chemistry you have like pH buffers. So like electrical circuits, the ground is your like electrical like charge buffer. So it's just like discharge. It's like yeah, it's quite cool. So yeah, so over here V equals 0. Okay, well, what's next? So we have one unknown voltage here. I claim that once we know this E here, once we know E, everything else falls into place. Um, because um uh because like once you have E, you can find the current and voltage here. Because like the voltage is just E for these two guys. And the voltage here is just 12 minus E for this guy. And like once you have the voltage, you can find out the current, everything falls into place. So let's see. How do we find this E here? Guys, any ideas? I'm gonna put on my Dora hat, ask for ideas. Any ideas how we can solve for E? What equations should we write down? So notice how I say like there's n minus 1 equations. So over here, n minus 1 equals 2, right? So two equations, but we have only one unknown. Why do we need two equations? One of the two equations also includes this. So this because yeah, like this is just like you just know it. So yeah, like, I said like this is so I wouldn't say the equation. I would like to say like pieces of information. So you only need n minus one additional pieces of information about the circuit. So you already have one more piece of information. You need one more piece of information here. Um, yes, yes, no. Uh, okay. So one more thing is that you realize why there's a minus one. So another good way to see why there's n minus one is because you can always just choose anywhere to be zero. So that's kind of like unconstrained. So, like there's two ways to see like why it's n minus one lah. One way to see is that you can always just randomly choose any point to be zero, or it's like some graph theory shit. It's literally some graph theory shit. That you could like that you can like generally prove. Um, so okay, voltage drop from 12 and voltage rise from 0 given to. Oh, true, but like how would you find that though? Zhongwei. As like how would you put that into equation form? Okay, so I think a big hint is that over here, the whole motivation behind n minus 1 is because it's a Kirchhoff's current law. So it should be KCL. So not KVL. It should be KCL. So let's take a look. So you write KCL at this node. You write KCL at this node. So you write KCL at this node, you get KCL at so let's call this like N1, N2, N3 lah. Because like in the future, if people read my notes, like N1, N2, N3. Symmetry. What does that mean? Like you like point inversion. Like what is it? NP dot append K. What? That's crazy. Oh, you mean like you flip the V? So are you saying you like KVL? You flip this by symmetry, you get KCL? Is that what you mean? So hell yeah. I feel you, bro. I think you're onto something. So so anyways, like you write KCL at that point. How would I KCL? So KCL means KCL means current in equals current out. Currents are determined by the signs of the positive and negative, which are arbitrary. So this in and out idea is just kind of arbitrary as well. But over here, what I like to think about it is like this. It's like 12 minus E divided by 2 ohms. So it's this. So I say that you look at this and you look at the current going into this node, the current going into this node. So the current going into that node is just like this voltage drop divided by the resistor. So that's how you write Kirchhoff's current law for the input current. And so you set this equal to the current out. So in this setup, because we set this up so nicely, there's two things. So there's a 2 amp that like the 2 amp just constrained. So like there's always a 2 amp here. Plus the current going out here. So what's the current going out here? The current going out here is V over R. So it's uh, E minus 0 over over 6 ohms. So now you have one equation, you have one unknown, you can solve it. Which is like so nice, right? Like you set everything up so nicely and then you can just like solve it immediately. So instead of solving eight equations at once, you solve this one equation for E. So E, okay, let's solve this together. It should be quick. 6 minus E over 2. You want to multiply everything by 6. So 6 minus 2E total plus E equals 6 volts. Right, so E equals 6 volts. This is very real. So you know what? You might be onto something. But like because of something else, I realized about something about this circuit, but like it's a later comment. So when we get there, we'll get there. But like I would say like why it's symmetrical. Um, so you're not wrong. This circuit, like this actual circuit, this I mean like no bullshit or like no bullshit aside, this circuit is actually quite symmetrical. So um, we'll see why. But um. Well, yeah, we'll get that later, but it's something called Thevenin and Norton. Like if you actually like Tevenize this circuit, you realize that it's actually symmetrical. But don't worry about it. So, anyways, I did not. Yeah, so so yeah, like that's how you use a node method. The node method basically how it works is that you set one node equal to 0, and you like assign voltages. If you know what voltage it is, you set that equal to like whatever voltage you know, and then you solve it. And then you have like the most equations that you will need for this method is n minus 1. And then you will know all the voltages at every node. Once you know that, then you can like solve for like individual components. Like for example, now you know this voltage drop is E, the current is whatever. Now you know this voltage drop is 6. Um then the current is like 6 divided by 2 is like 3 or whatever. So it's like now you know the voltages, you can individually assign voltages and currents to every component you have. Okay, so any questions up to this point? Do you guys want a practice question or should we just move on? Because I think like we're less time. The handout should have practice, but if you want to do it now, okay, cool. I would move on. Before then, I would like to take a break. So, what do you mean symmetry? Where if the problem has symmetry, what symmetry? Wait, like what kind of symmetry are you talking about? Are you talking about algebraic symmetry here, like the symmetry in the variables, or? Huh. I'll send it to you when I find it, but I don't think I have one off the top of my head. But yeah. So let's take a break. We'll come back in like 2 minutes, 9:02, 9:02 p.m. Come back. The rest for 2 minutes because I've been yapping. Wait, so 6 ohm and 2 amp current source in parallel? Oh, well, I mean, if that's how you want to interpret the equation, then okay lah. But I think what the equation is trying to imply is that, wait, don't take the equal sign too seriously, because this equal sign comes from the conservation. So it's not saying that 6 ohm and 2 amp current source in parallel is equivalent. So we're not saying that this is equivalent to this. We're not saying that. We're saying that the currents going through both of them is equal to the current going through this way. So that's why we're saying that. That's what the equal sign is for. It's not saying that these two setups are equivalent. So yeah, we're saying that the total current through here is equal to the current going in from here. We're not saying that these are the two same things. Like these are different. These are different things. Is that okay? What do you mean the symmetry? Wait, what? Am I not seeing a symmetry here? Like, what symmetry are you guys talking about? What, what symmetry? Like the point inversion of like the what, like the rotational group or something? Like you rotate the whole thing, you get the same circuit. Like what? What? Am I missing something? Anyways, okay, so it's 9:02. Okay, let's come back. Don't. What do you mean? Just think about it. Like you think about it. Okay, wait. So next, superposition. Okay, so superposition. Okay, so um, for a little while, I want to like take a step back and assume that we don't know anything about this voltage. So I want to make this general. Suppose I don't have this like 12 volts. Suppose I call it V. Suppose I call this I. Okay. Suppose I call this V and I. So okay, I'm gonna solve this circuit for um the current through this guy, for example. So okay, actually, yeah. Suppose I want to solve for the current through this guy. So in terms of V and I, so I would still do the node method. I'll call this like 12 volts. I would call this E. I'll call this 0. But then it's like not 12 volts, like just V volts. So node method on this end, node method on this node, KCL on this node would give me V minus E over 2 is equal to E over 6 plus I. So notice what I'm doing. I'm trying to take the result from earlier that we just like, I mean, because just now we saw that, okay, you can do this node method thing. You call one node equal to 0, and then once you have this potential, you can kind of like solve for everything else. So now I'm doing the same exact thing, but instead of plugging in V equals 12, instead of plugging in 12, I'm putting as in some general V, some general I. I'm trying to show a point here. I'm trying to prove a point here, but like, hear me out. So, once I solve this, so it's going to be 3 volts minus, sorry, 3V minus 3E is equal to E plus 6I. So 4E is equal to like 3 volt minus 6I. E is equal to 3/4 V minus 3 2I. Okay, so, okay. My point I'm trying to make is that like whatever circuit you have, if it's only made up of linear components, linear in the sense that if it's a current source, voltage source, resistor, capacitor, inductor, the well-behaved components will always give you the voltage, will always give you results that are linear combinations of the sources. The results can only be linear combinations. So it can't be V squared. So like for example, you will never see this in a circuit. Like if your circuit is made up of linear components, like resistors, current sources, whatever, everything is linear, you will never see a square. You will never see a sign. You will never see an exponential. I mean, you will in like a circuit case stuff, but so actually forget about capacitors and inductors for now. But just remember that those are also called linear components. But if you have a circuit that's made up of resistors, current sources, and voltage sources, there will always be like everything will always only be linear combinations. As in like it's always gonna be linear combinations of the sources V and I. And this can be general. Like if you have like 10 voltage sources, that it's gonna be the linear combination of like V1 to V10. So it's all gonna be linear. It's not gonna be like V squared, no exponential decay. I mean, in the time dynamics there is, but like, that's not really what I mean. It's a different kind of, well, I mean, it's a separate case, but like, just know that this also holds for capacitors and inductors. So yeah, it's a separate case. Anyways, so here, my point is that you realize that it's a linear combination. It's a linear combination. So why not we turn one thing off and we solve it? So what do you mean by turn? So okay, as in, so what I'm trying to say here is that there's a sneaky thing you can do. There's a sneaky thing you can do. So you can like, so you can call this E1 plus E2. The sneaky thing you can do here is to turn one thing off and only find E. So suppose now you turn off the current source. You turn off the current source. Then E is gonna be E1. So why would we do that in the first place? So why would we do that in the first place? So okay, before that, when we say turn something off, what do we mean by that? You guys have an idea? So like we're trying to do something sneaky here. It's a very powerful idea that I want you guys to like kind of like reason about. So we have a sneaky, sneaky thing that we're gonna do here. So suppose I want to turn off the current source. Suppose I want to set I equal to zero. I want to set I want to set I equals zero. What can I do to this circuit to like effectively turn it off? Yes, rip out the current, right? Exactly. So, um, how do you rip out the current? Like, do you just straight up take it away like this? No, do not add another current. No, so you straight up just make it an open circuit. So when you want to set the currents equal to zero, okay, so let's think about it from a higher level. When you want to turn something off, there's only two things you can do. You either replace it with an open circuit, or you replace it with a closed circuit, right? You either replace it with an open circuit or a closed circuit. Why is it an open circuit? So over here, if you want to turn off a current source, you replace it with an open circuit. So the reason why you replace it with an open circuit is because like once you rip it out, like as like once you replace it with an open circuit, no current can flow to that point, right? Like I mean, if there's electrical discharge and like like stuff like I mean realistically this like well, I mean realistically in the real world like it depends on what you mean by like rip it out. But like, in this theoretical world where you draw circuits and like as lines and sticks when you turn everything into when you take something out when you replace it with an open circuit, there is no current that can flow here. There's no current that can flow here. So that's why I equals zero. And so the volt so notice again, remember what we said here. These components constrain something. Current sources constrain the current, but doesn't constrain the voltage. The voltage can be whatever it can be. If I turn off if I turn off the current source, the current cannot flow. There's no current here, but it doesn't limit the voltage still. The voltage can still be whatever it is, right? So this is gonna be E1. That's what we call E1. Mhm. And so we solve. Sorry, the body. Okay, so let's solve for E1. Okay, let's see. E1. So V minus E1 over 2 is equal to E1 over 6. Yes. So E1 is equal to E1 is equal to 3 over 4 volts, as we expected, right? Okay, so that makes sense. Let's come back over here. So remember what we're trying to do here. We're trying to do something sneaky. And what I'm trying like what I mean sneaky, like I'm trying to say that since we know that E has to be a linear combination of the input, like the energy input, energy sources. Um, so because it's a linear combination, we can actually turn everything off and only look at one guy at the same time, at once. So this is a very powerful way to do things because like if you have like 100 different sources, if you have 100 different like voltages, it's gonna be hard if you take into account everyone at the same time. But if you can like individually like only so you know how like when you do has anyone like mixed music before? Has anyone made music before? Actually, I think that's a hard like this is a big question. But has anyone made music like with a digital audio workstation like a DAW? So what you have? So wait, okay, so like you know how like you can like solo out a signal. So it was just like you have like 10 different tracks playing and you can solo one guy. It's the same thing here. Like you have 10 different voltages, you solo one guy. So stop. Where where's this symmetry coming from? So oh my god, my throat's killing me. So yeah, so you can actually just like single out like one source at once. You turn everything off by like replacing that with like open circuits or closed circuits. I haven't gotten there yet, but like you turn everything off and then you only look at the contribution of one guy. You look at the contribution of one guy, one guy, one guy, one guy, and you add everything together, and then you get like the total voltage. Um, so mm. Okay, so over here. Now we want to find E2. E2 is what happens you have uh when you turn off the voltage. So suppose you turn off the voltage. You turn off the voltage. You set this equal to zero. What should we do to the voltage source? Should we replace it with an open circuit or a closed circuit? Okay, I want you guys to think about this for a second. I don't want you guys to answer right away, but like think about it for a second. And then um in 9:15 in a minute, I'll ask you guys to like tell me what you think. Okay. Should we replace right now we want to turn off the voltage source. We want to turn off this voltage source. Should we replace it with an open or a close? That's a question. So yeah, think about it. I'll ask you guys in a while. Is it a good question because it's symmetrical? Mm-hmm. Is it? Of course. I figured. Mm. All right, so it's 9:15. What do you guys think? Should we replace my life savings? Okay, so should we replace this voltage source with a closed circuit or an open circuit? What do you guys think? Bro, I have like one loyal fan. Thank you, Jovan. Yes, okay, Lucas, thank you. So, yes, closed. Okay, yeah, okay lah. Like, so answer is close lah. Okay, so what, what is the symmetry thing you guys are talking about? Like what is it? So let me erase this red for some reason. Wait. So yeah, when you want to turn off voltage sources, you have to you zero them out by making them a closed circuit. So you replace this with a short. So you replace it with a short. Yes. So why is it a short? Because let's come back over here. let's come back over here. So this is kind of counterintuitive. Like normally people would think like when you take something out, you replace it with an open circuit, but over here in a voltage source, in this theory land, like cow in a vacuum kind of thing, uh, the voltage sources, if you turn it off, it will be a closed circuit. In the real world, if you like turn off a battery, like it's actually just an open, like like in this sense, when we say like mathematically turn it off, we actually mean to replace it with a short. And why a short? Because if you turn it into a closed circuit wire lab, a closed wire, these two nodes are the same potential. These two nodes have no voltage difference. These two nodes have no voltage difference. So when you set V equals zero, you're actually creating that short effectively in theory land. So in theory, when you create when you turn off a voltage, it becomes a short because um suppose you have some battery here. So like let's say suppose you have some battery here. This 3 volts. This battery makes it like 9 volts. So that's like this is a 6 volt battery. So it goes from 3 volts to 9 volts. If you turn off the battery, if you turn off the battery, this thing only stays at 3 volts, right? Mathematically turn it off. So it will just become like a short. 3 volts, 3 volts. So that's like the non-symmetry way to look at it or something. And it still doesn't constrain the current. The current can still flow. The current can be whatever it is. You're not constraining the current. So current can still flow here. Current can be whatever it wants. Cool. Okay, so E2. How do you find for E2? So E2, again, using our node method. So this is 0. So 0 minus E2 over 2 ohm is equal to E2 over 6 ohm plus I. So solve this. So E2 is going to be negative 3 halves of I. Does this make sense? Does this make sense with what we expect? Yes, it does. Yay. Hola, soy Dora. So it is the same thing. It is what we expect. So this E1, this E2, and that's what we've realized here. So the moral of the story is that like you can superpose circuits together. You can do so. This method is called superposition. So you can deconstruct anything in the circuit into like contributions from sources. So yeah, this is called superposition. Superposition is a very fancy name, but basically what it means is that you can like superpose things on top of each other, like by adding them. So um over here in this case, we're doing it in reverse because I'm trying to show you guys like how it works. But in practice, if you want to do superposition on the circuit, you're given a circuit, you mentally you turn one thing off. So I mean you solve it by turning one thing off and solving it for the effect of something else. You turn this off and solving for the effect of this guy, and then you add both effects together. So that's what superposition means. You can do superposition on any circuit, any linear circuit at least. So yeah. Okay, any questions? Okay, yeah, big day for math nerds, for the people who see the symmetry in life. Anyways, so next part. Um, Thevenin. Okay, so Thevenin is also one of the things I like. So I like this circuit a lot because I can just reuse this. Um, Actually, you know what? Let me just copy this. Oh wait, actually, yeah, sorry, I forgot to label this. So this method is called uh superposition. Okay, now let's talk about Thevenin Norton equivalence. So this one is like when you kind of make shit up. So so you know how, like last week okay, did Yongshun talk about image charges at all last week? Because I totally did not have the recording for people who were there last week. I wasn't there last week, so I have no idea.
He
Oh,
slightly did.
oh, he did. Okay, image charges. So like you remember what we did in image charges? Like you have this like setup. You have this like physical true setup of like electrons and like infinite conducting plane or whatever. So you have like a conductor and an electron or like a charge. Mm. But because of the uniqueness theorems, you can just make shit up and say that okay, there's an anti-charge on the other side, and then it is very symmetrical, yeah. So but the reason why we're doing this is because like for the charge and the conductor, there's some there's a boundary condition that um both conditions satisfy. As in, like mathematically, both are the same thing, and so you can replace one setup with another, and they will work. Okay, over here. Um, let's see. Okay, suppose I'm trying to. Okay, so let's change our view on the circuit a bit. Let's change our view of the circuit. Shit. Suppose this circuit suppose this circuit is used to supply energy to this middle box here. So as in, like just now, this in this box we had 6 ohm resistor. Right? Just now in this box we had a 6 ohm resistor. Suppose this whole circuit actually no, wait, hold on. That's a bad idea. Okay, you know what? Let's just do this. Suppose this circuit is used so in a black box. Suppose this circuit after like some engineer designed this shit, and then you use this to supply energy to something else. As in, you can ship this out and be like, okay, this is a new component. So this is a new component that I made. There's some voltage and then some current. I'm following like the sign convention that we had just now. Like current always flows in from the positive side. Remember here, current flows in from the positive side. Okay, so oops. Okay, physically, what does a circuit do? Physically, what does a circuit do? If you okay, let's see. Okay, how can I explain this? Okay, so if I connect the circuit to some other part of the so if I connect this a black box to some other component, for example, a resistor, um, if I connect this to a resistor, how would this circuit behave? How would this circuit behave? So as in, like, suppose the resistor already has like response by giving V and I lah. Suppose this I and V are effects coming from some external thing. So it's like, okay, I have this black box. I connect it to a resistor. This resistor responds by giving this V and I. So as in, like, what I'm trying to say is that suppose I'm given some general V and I connect this black box to something else. The black box receives this response of like V and I. How does this V and I relationship work? What as in, like, so what I'm trying to say is that what's the IV graph of this quote unquote effective component? Right. So this whole thing is an effective component now, right? So what's the IV graph of this effective component? Okay, so that's the question here. So let's see. We can analyze the circuit, albeit it's a little bit more nuanced stuff. So let me copy this and like, so I can destroy it. So if I still use a node method, so this is 0 volts. So this is 0, this is 12. Um, so this is V. Okay, so 12 minus, say, KCR at this node. Let's do KCR at this node again. Okay, KCR on that node. So 12 minus V over 2 is equal to, okay, coming into the node. So that's also I. This is equal to V over 6 plus 2. Okay, that's how, so I wrote the KCL for this thing. And so once I solve this, oh my God, okay, give me some time to solve this. 36 minus 3V plus 6I equals V plus 12. So this 4V is 24. So we divide both sides by 4. So V equals 6 plus 3 halves. Okay, so yes. So the IV graph will be this. Okay, so let's take a step back and like remind ourselves what we're doing. We have this circuit, and we're using it as like, so suppose we're using it as like powering something else. Like it can, so I'll talk about like another case where this is like relevant, but like, for now, assume that we're using this as a component, like as an effective component. So as an effective component, you um you like, so yeah, so you treat this whole thing as a black box, and you connect the two ends. It will respond with a very specific IV curve. It will respond with a very specific IV curve. So what is an IV curve again? Remember, an IV curve characterizes this behavior. An IV curve characterizes this behavior. So an IV curve of a voltage. So IV curves is equivalent to knowing the voltage behavior. So knowing the IV curve of a component tells you um the role that the component plays in the circuit. So for example here, resistors have a constant slope IV curve. Voltage sources have a constant line in the IV curve. Current sources have a constant line in the IV curve. So same thing over here. If you want to know how this mystery component works, we will have to know its IV curve, which we just got here. So V will be equal to 6 plus B halves R. Okay, I want to be a little bit sneaky and say that we actually don't need all that shit. We actually don't need all this stuff. We actually don't need all this shit. So if I wanted to construct, so if I'm like, I want to be a Chinese seller. So like this is some like Russian made like high grade military stuff, right? So I want to be some Chinese seller. I want to make a really cheap Chinese product. How do I save money? So if I want to save money, I can actually like reduce the number of components I have. So hear me out. What if I make a black box with 6 volts and 1.5 ohm, and then I just ship this. So suppose I make a like less complex circuit and I ship this. Oh, does this work? Does this work as a component? So outside of the black box, I actually still see the same thing, right? Like outside the black box, I actually just see like the two ends outside. I actually just see this. And then if I do experiments, okay, so what happens if I have zero current? If I have like a open circuit, if I just measure this across the terminals, I'll get 6 volts, which is like what we have here. If I turn off this current, I'll have this. Um, if I replace this with a short, if I replace this with a short, so V will be 0, and I would be -6 times 2/3, which is -4. Is that true? So is the current like -4? So I is just like the ratio of the simple. Yes, it's me -4. So yeah, this circuit actually achieves the same thing. Okay, so I won't like I mean it's up to you to verify for yourself lah. I want you guys to verify for yourself that this is actually the same thing as this circuit. These two things are equivalent circuits. These two circuits are equivalent circuits. So yeah, effectively you can save components. And yeah, another big W for China. W's in the chat, guys. W's only. Thank you, Jongwon. You're my number one fan. Yeah, so yeah. So my point is that you can actually see you actually see that you can reduce the complexity of a circuit into its equivalent part by thinking about its IV curve. So there's a way to speed up this process. This voltage here we call the Thevenin voltage. So this voltage here we call the Thevenin voltage. Oh, sorry. By the way, this reduction is called the Thevenin equivalent. So this is called the Thevenin equivalent. So Thevenize. So this is called the Thevenin equivalent. So this is called the Thevenin voltage, and this is called the Thevenin resistance. VTH and RTH. Okay. So this is the voltage version. If I kind of like rearrange this formula, if I rearrange this formula, I can actually get something else. So what if I rearrange this formula and I is equal to um, 2/3 V minus 4. 4? 4, yeah. 4? Yes, 12 minutes. Sorry, I'm tripping today. So let me rearrange this. -4 plus 2/3. Yes. So if I rearrange this equation, I actually get this form, which is like the same thing. These are the same IV curves, by the way. So I'm just like rewriting this equation. These are the same equations. These are the same exact equations. I'm just rewriting them. So once I rewrote them into this form, you can actually realize that there's another way to make this cheap Chinese product. I can actually just make this. Sorry. -4 amps, 2/3 ohm, and call this my circuit. So this circuit is called a Norton equivalent. So Norton means the current equivalent lah. So this is the Norton equivalent of our circuit, which still has the same IV response curve. It still responds the same way. This IV, it still responds the same way. Uh, maybe. I'm not sure if it's symmetric enough for a free antivirus software. So why 2/3 ohm? Oh sorry, my bad. Sorry. It should be 1.5. My bad. You're right. It should be 1.5, not 2/3. Um, but yeah, like the point is that like you can also make a Norton equivalent with the same so yeah, with the same Thevenin resistance. The Thevenin resistance will be the same. The same I sorry, I inverted it just now, but like it will be the same Thevenin resistance, but now with a current source. Now with a current source instead of a voltage source. Why is this useful? Why is this useful? Oh, okay. So But okay, like before we talk about why this is useful, does this make sense to everyone? Like, so essentially this boils down to like the uniqueness theorems. Like if you actually like write down like this is actually equivalent to the uniqueness theorems, and if you can find another circuit that does the same thing, you can actually replace it with that circuit. So this is called the Thevenin and Norton. Yeah, it's the same. It's the same. Yeah, so that like as Joel mentioned, as John Wayne mentioned, like there's a uniqueness theorems last week. This is the same thing. V over R equals what? Yeah. So yeah. So yes, that's literally why I said. So okay, any questions on this? Let that sink in. Okay. I'm actually eating biscuits, so that's why I stopped talking for a while. So okay. Um, I actually think they were all good. Um, there's something that I wanted to teach you guys about resistor tricks because okay. Um, let me let me go use the restroom and wait. I'll let you guys think about this for a little bit more. I'll be back in like 2 seconds. Uh, yeah, I'm sorry guys. The nose was like killing me. As if you can tell, I'm kind of sick today, but I feel great. I feel great. I just like my body's just like not feeling great. Anyways, so yeah, coming back here. Um, something I would I that's not really like something that electrical engineers would learn. But it's more like a math trick that physicists learn like along the way. So which is like resistor tricks. So equivalent resistances tricks. So, um, let me just because I wrote this problem a while ago. Um, I'm gonna post it in the chat so I can copy it over. It's kind of cursed, I know, but like you need a Zoom chat for this stuff. Um, so I wrote this problem a while ago. Okay, that's me. Uh, let's copy this. Save image. Allow. Thank you. Let's paste this here. Yep. Okay. Um, notes. It, it doesn't. Okay, wait. Let's just look at some of these. So let's see. I don't remember which one goes for which one. Mm, let's get four. This one is from an I4 question, by the way. Um, yeah. So, um, this. Let's see. Oh, let's do this one first. So, Actually, yeah. So what my point here is that one tr so this is not really like a talk. I don't really know what to call this, but it's like a equipotential trick. So it's one of the Olympiad tricks where you can simplify things really quickly. Because when potentials are the same, so okay, let's back up for a bit. Like right now, we want to find the equivalent resistances. Okay, let's do this one first. Okay, let's do this one first. Um, right now we want to find the equivalent resistance between this end and this end. So as in like if you have a voltmeter, so if you have an ohmmeter, you want to measure the resistance, you connect it to these points. What will you measure? So what would you measure? So over here, there's some there's some symmetry here in this system. So like you see that there's some symmetry in the diagonal direction, right? In this axis, there's some symmetry. Um, so when I say symmetry, it's also symmetry in the values of the resistor as well. For example, here, if you suddenly have like 10 ohms, then this stuff is not gonna work. This shit is not gonna work if it's 10 ohms. Um, you could kind of like massage it into something that works, but like, it's gonna be hard. Like straight up, just like, don't do that. But if it's symmetric, which is most of the cases in physics Olympiads, um, you know, that's why that's why it's like nice to talk about here. Um, is yeah, there's some you can exploit that symmetry, like actual symmetry here. So the trick here is that when things are equipotential, when points are equipotential, you can actually link and unlink them. So yeah. So let's think about how an ohmmeter works. Let's think about how an ohmmeter works. The ohmmeter is going to inject some voltage. No, sorry, it's going to inject some current and then measure how much voltage there is, right? So if you inject some current into here, and then you measure the voltage across these two ends, then you can like, take the ratio and you can get the resistance. Um, so yeah. Um, More importantly, we're talking about voltages. So let's call this voltages here like V like 0 and V lah. Okay. So for simplicity, like because of the node method, we know we can do that. Um, so you realize that whatever this voltage is, suppose I call this E lah. Okay. Suppose I call this E. The electron can also an electron that's starting from here can actually or like starting from here can actually like take the same path to get to E. It can also take the same exact path that's symmetric and also get to E. So the voltages here are symmetric. The voltage, um, so suppose E1, so this E2. So these are all symmetric voltages, right? There's some symmetry here. So this E3, for example. So these are all symmetric. Um, the trick here is that you can collapse all these points down into one node. So you can collapse this. So suppose I draw, yeah, I lazy already lah. I'm drawing this lah. So imagine every line is a resistor. Okay. So this is the original circuit. So this is the original network of resistors. What you do is that you like squish them, you squish these two together. You squish this node and this node together. You squish this node, and this node together. Oh, sorry. Oh, squish this node. Mm, am I tripping? Um, no, yeah, I'm not tripping. Um, yeah, squish this node, and this node together, and squish this node and this node together. Um, so once you do that, you actually obtain. mm, so once you do that, you actually obtain this kind of thing. So we want to measure from here. Um, does that make sense? Like how I collapse this? Because once I collapse this, like once I collapse this down, I get this node. Once I collapse this down, I get this node. Once I collapse this down, I get this node. So that's like three nodes I got in the middle. And there's four because like there's one, two, three, four. One, two, three, four. So yeah, I collapse into this. And so yeah, like it's easy to like find the equivalent resistance of the whole thing now because it's a 6 ohms, 3 ohms, 3 ohms, 6 ohms. So altogether, like you add them together, you get 18 ohms. So that's how you can quickly find the resistance here. Like you don't have to like inject. It's like once you get the trick, you can actually just like right away see it. Um, yeah, I know, right? Done. It's quite quick. So it's like one of those tricks that you like. So the trick here is to realize that nodes of the same voltage. So this was also the same voltage. The trick here is to know that like nodes of the same voltage can be collapsed down to the same point. When you're doing these like resistor combination things. Um, you can also do the same thing. Actually, no, you can't do the same thing. What can you like? I'm not sure. But yeah, like normally what people use this trick for is here. In this like resistor equivalent resistance kind of problems. So over here, suppose you do have well actually no, like yeah, wait, I think we don't have time for this. So, like, yeah, you guys can like because I should be sure. You can also check the IFO problem now. So this thing I took from Wang, this thing I took from IFO. But yeah, you just check IFO solution. 20 like 19 something I think. Anyways, this you can do it without this trick, but you can also do it with this trick. So it's an equipotential trick. Um, actually no, sorry, I don't remember if that question has the equipotential trick, but yeah, there's like more problems that have this equipotential trick. Now I can just post in the handouts in the future. Um, so yeah, let's see what else. Okay, last thing, AC. So AC is a bit it's a little bit of a long topic, but like I'm trying to condense it and like get the essentials here just for you guys. So in AC, um suppose I shit, not this, bro, I don't want this. Um, yes, give it to me. Yes. Erase. Yes, okay, cool. So AC. Suppose like it's easier if I just have like one source. Let's modify this. I don't know, 4 ohms. Oh, you know what? Like, let me just make this capacitor instead. Okay. So in AC, the voltage varies. In AC, the voltage varies sinusoidally. Um, so well, let me write something down. Okay, oh, sorry. Yeah, so in an AC circuit, the AC voltage varies sinusoidally. So normally people like to use cosine. You can also use sine, but that's just gonna be cursed. Like cosine is like more easy to work with. I mean, it's not easy to work. It's the same thing, but people like to think in terms of like cosine lah. Um, so uh, actually no, wait, before that, before that, let me introduce so actually before like way before this, I'm getting way too ahead of myself. So, like, forget about AC for a while. Let's put this in the corner. Sorry about this. Components. There's two new components that we haven't talked about. which are capacitors and inductors. So capacitors and inductors. Okay, so CL. Okay, so what do they do? Again, they still obey the same passive sign convention. So, passive sign convention. They still obey the same passive sign convention. Um, what's different is that unlike a resistor makes sure the resistor makes sure that the ratio stays constant. The capacitor makes sure the ratio between the time derivative of the voltage is same as the current. So as in sorry, that's right. Oh yeah, sorry, that's right. Um, and in an inductor, it makes sure the ratio between the voltage and the rate of change of current is the constant. So as in what I'm trying to say is that it's constant. Yeah. So as in like this is what the components do. The capacitor makes sure this thing is constant. The inductor makes sure this thing is constant. Um, yes. So, okay, any questions on this? Um, okay, well, like actually, like I think there's one question on this, like where would this come from? Um, these these things will come from like the reason why we draw them like this is because like we first discovered them in terms of we first discovered them in terms of two metal plates and just a lump of wire. Um, but Um, yeah, afterwards, like these can be like describing anything at all. They don't have to be two plates together. These two are general ideas. These two are general ideas. Like how do you make a capacitor? How do you make an inductor? So unlike a resistor like it's like a extreme case of a conductor in the sense like it doesn't conduct the best. But it's a conductor. You can actually do stuff with it. Um, but resistors can also like so just like resistors, capacitors, and inductors, they can also be used to model general things. Like as in, you can model like a cable. You can model like a huge, really long cable as like a combination of infinite inductors and capacitors, like a coaxial cable. Like a coaxial cable, you can actually this is a thing that like network engineers the like I don't know wasn't it, this some engineers use model um like transmission loss. Like these things are like models. Like you don't have to like have an actual piece of wire making an inductor. Like literally you can have fabric be an inductor. Um if you know like you have um enough um enough like if you have enough fabric of them lying around. Because actually no, I think fabric is a bad idea. Uh cables, sorry, yeah, cables. So if you have a really long cable and you coil them up, you can actually make a inductor. But you don't have to you don't have to how do I say this? You don't have to have a specific component that's an inductor to be an inductor. That's what I'm trying to say. Um, so yeah, well, I mean, HRK has examples for this. I don't think Fabric can. I think that was like something I just like really thought of. Um, can it? No. There's like conductive fabric, which is different. But like, I don't know why I said that. Um, hmm, interesting. Anyways, so I think it looks cool though, like, doesn't it? Um, so yeah. Okay, why are we talking about like capacitors and inductors before this? So in AC signals, you assume that voltages have sinusoidal varying components. So No, I was like trying to think of like coiled things. I was trying to think of like coiled like things like wires, but I don't want to use wires, so I said fabric. But then afterwards, like fabrics are like insulators in the first place, so it was a stupid example. Anyways, um, okay, maybe keychains. Like maybe keychains. Like you know like the keychains have those like loop things. Like so if you have like enough of them like coiled together, you can also make an inductor. Um, or just like a piece of like metal ring can also be an inductor. Like just a ring of metal is also an inductor. Like anything that should be conductive. I think like fabric was a bad idea because it was like a non like it's an insulator. Yeah, I'm not sure why I said that actually. Um, but yeah, anything conductive should be able to make an inductor. Um, but yeah, anyways, coming back to AC. Um, normally, so we look at sinusoidal signals, and normally what people do is to say that okay, that's a real part of a complex number. So hopefully you guys have seen this, e to the j omega t. So j is the imaginary number here. Sorry, not display. J squared equals to -1. Mm. Yeah, uh so if you haven't seen this before, like you should check out the math lecture. Um so why this? Because this is easier to work with. So if you have an exponential, it's actually easier to work with because when you take a time derivative, so if you take a time derivative of this, if you take a time derivative of this, so you get like negative v naught omega sine omega t. It's kind of like you can still work with it, but like the cosine the cosine Hilang already it's like not the best to work with because ideally you like to work with the same thing. Like what if you add this to another cosine? Like you can't add the cosine and sine together. I mean you can, but there's gonna be some phase shift. So however here, um if you take the time derivative of this, you get this. And you still have this e to the j omega t. So it's still like like as in you still have the same signal. Like you just multiply yourself by j omega. So essentially in this world, the reason why we like to use this kind of version of cosine is because when you take time derivatives, it actually becomes a multiplication. So essentially, the time derivative of this like v tilde that I'm writing here. No, let me just, I don't think we have time for this. Like, let me just go like have a high level overview. So the time derivative of this like this v tilde, it's gonna be j omega v tilde. So that's why we like to use the exponential version of these things. So these things are called phasors. Phasor. So I think it's a phase vector or something. That's why it's called a phasor. It's like a phase vector. It's like a vector in complex space that points in different directions. So um, yeah, so like that's why we like to use phases, and I think the standard way to like after this is to just use like phases and like treat so treat AC as like a DC voltage with like so I think the way to think about this is to treat AC circuits the same way as DC circuits, but with complex voltages. Yes, that's the right way to say it. And that's what people do. And so because of this, so C, remember how we said C is equal to I over dV dt. So this is actually just gonna be so the thing is, um, we want we don't really like this kind of definition, right? It's kind of clunky. It's kind of clunky. So I promise this is gonna be the last part of today's lecture. So okay, I'm gonna end up quickly. Oops. The VDT, as you just saw, is actually just J omega C um, V. We call everything the tilde. So remember, like the effect of this time derivative thing, this time derivative business, you can actually just replace with J omega in a complex case. So over here, if you put everything as like complex current, complex voltage, um, then we can have these relations. And so you realize that V tilde over I tilde. So why are we looking for V tilde over I tilde? It's because, as I said just now, when you want to solve an AC circuit, now this idea of like phasors, you can actually just solve AC circuits the same way you solve a DC circuit um with complex voltages. So so over here we want like a complex resistance, kind of like resistance, but it's not really resistance. I'll put in quotes for now. Um, so this pseudo resistance, um, we call this phi, so it's 1 over J omega C. For inductor, this pseudo resistance is gonna be J omega L. So um also two things. Now that you have like this like quote unquote pseudo resistance, um, well, I think pseudo is a bad word. Pseudo means like pseudo implies that it's fake. It's not really fake. It's an actual thing. So it's an actual thing that you can measure and whatever. So people actually call this the impedance. The impedance of a capacitor and an inductor. So the impedance, this idea of an impedance actually hinges on the fact that we use phasors to model to model AC. If you don't use phasors to model AC, if you say that well there's this whole like signal like processing idea of like Fourier analysis, um that basically like anything can be broken like in sine wave, so like you can always write it as a phasor. Uh but yeah, so yeah, so these are ideas that will hold regardless of what signal you're using. Even if it's non-AC, even if it's like a signal pulse generator thing, um you can still use these formulas for impedances because a long time ago some guy called Fourier said that you can do this. Um, but yeah, I guess like I think we're 5 minutes over. I will stick around for any questions, but thank you for coming today. To recap, we talked about solving equations by brute force, the node method, superposition, determining Norton equivalence, and kind of finished off with some random ideas that like, you'll see in the Olympiads. And then yeah, we didn't really have time to go through all of the AC stuff, but like, next time. Oh, actually, no, no more next time, but like, it'll be in the handouts. And I'll also be in the chat if you guys have any questions. So yeah, great night. Yeah, bye. I will stop the recording.